Hi there, and welcome to your first 3x video. I just want to have an introduction on why we're using these videos and how you can use them most effectively. If you noticed or have heard, 3x is a very rigorous class, but very doable. We do have a lot of material and great material, but sometimes we need to slow down a little bit. And I think that's where these videos are going to be great. They are going to require some work outside of class, but not much more than you would normally have if I assigned a homework assignment. What's great about these is you can fast forward them if you've seen it before. You can stop them, maybe take notes if I'm going too fast in the video. You can rewind them. Maybe you missed something, a little key aspect that I used later in the video, and you can rewind it. And I want you to use all these advantages. As you'll notice, as we talked about in class, there's going to be some expectations from the videos, maybe a couple problems, maybe some notes that you take that I'll be checking the next day, and that's pretty much what your homework is. I want you to come in with a little bit of knowledge on our next topic. So then we can really have an effective class with each other to make sure we have that little bit of understanding, but I think we're going to have the time to get much deeper knowledge. It's going to be the same type of class that 3X is in any other class. It's just that we're flipping it. We're going to have our homework in class and our in class at home. So hopefully you enjoyed this flipped classroom. It's new to me, but it's going to be a great experience, I can tell. So let's get after it. I want to talk a little bit about what we did on the first day and see if we can add some new information for the second. All right, so let's quickly talk about what we talked about in class and what makes a good proof. This class is different from 2x in pretty much that sense. 2x was, here's the formula, plug and chug. There is definitely great teachers in our curriculum that teach the theories behind it, but 3x is going to be the difference. We want to know why things work. The biggest question I'm going to be asking you guys is why? Why? And I think that's the greatest thing about 3x. We are going to become problem solvers. Not just mathematicians that redo problems that people have done before, but see if we can really analyze what they were thinking and then see if we can extend it. You guys are going to be great problem solvers, and that's something that you can practice. So first we just have to have an organizational skill of what makes a good proof. One thing we talked about, it has to work every time. People have used their whole lives on things that they thought were just perfectly proven, and then we find one counterexample, and guess what? It's not accepted anymore. Step 2 is uses generalities. You're going to see that on the next slide. Instead of using numbers like 1 plus 1 equals 2, maybe we can use a general form of an odd plus another odd to see if it's always going to be an even. That's going to be so cool that we can go from one example and say, hey, maybe this works every single time that this situation works, but I'm not going to go through every example of an odd plus an odd. So we use generalities, and the next slide is going to be how we write those generalities. Now 3, pictures help, but pictures are interesting that sometimes they can prove something perfectly with some explanation to them. But for example, if I do this problem above here, let's say I want to do 3 plus 4. An example might be using what we call arrays, which are dots. So that's a 3, and then I'm going to have this 4 over here. We always try to make them rectangles, because if you think about it, any amount of rectangles, if I keep them too wide, is going to be an even number. But look at this. If I add these together, I have my 1, 2, 3, and then my 1, excuse me, I'm going to put this on the other side just to show that 1, 2, 3, 4, plus, I'm going to put the red in 1, 2, 3. Notice that I have this rectangle, plus the 1 out here. I kind of covered it up there. But that's an even, plus 1 more is always going to be an odd. So pictures help. They're great to solidify your argument. But a lot of times we're going to be working with these things up here in this class using generalities in our statement reason form. So let's look at how we actually write some of these generalities. And obviously, like, we're going to use the advantages of our video. We can stop and start as much as we want. But let's say we have 3 integers, m, n, and r. They could be any integers, not any number, integers. So we're just going to call them m, n, and r. Now what I want you to think about is, well, how can I always write them even? Not just if my m is 3, well, I can't just write it as m anymore.
So if you think about it, what the characteristics of an even number are, is they always have a factor of 2. So if we force it to have a factor of 2, maybe let's say it's 2m. Think about all the possibilities of m we can put in there. And always, always, always it's going to be even. Let's say it's going to be 2 times 1. Okay, that becomes 2. 2 times 2. 2 times a million, so on and so forth, is 2 million. It's always going to be an even number. So if we have an n, we can write it 2n. If we have an r, we can write it 2r. Here's a trickier one. Let's say we have any 3 odd integers. How am I going to write that? Well, I have the 2m. That's odd. Or sorry, that's even. So how our number system works is that if I get to an even, if I just add 1 to it, I'm at that next odd. So that's the form of an odd number. It's got the even part plus 1. So if I have an n, or I want a different odd, I can go 2n plus 1, and then 2r plus 1. All these would be 3 different odd integers. Now if m and n were the same, they'd be 2 of the same odd integers, but a lot of times we want different ways of writing them. All right, write 3 consecutive integers. Well, if I start at, let's say, n, some number, we use n a lot for just any random number, what's the next one going to be? Again, number system, n plus 1, and n plus 2. There's 3 consecutive integers, no matter where n starts. If I plug it in here and plug it in here, it's the same n. I'm going to have 3 consecutives. Now what I want you guys to do as a little bit of a challenge coming in tomorrow, I want to see if you can write 3 consecutive even integers and 3 consecutive odd integers. So that'll be part of your homework, which I'll check in class tomorrow. See if you can write 3 consecutive even integers and 3 consecutive odd integers. Now let's actually see where we can use this. I'm going to add a slide here to say, let's say I want to show that an even plus an even is even. Now I didn't say 2 plus 2 is 4. That would be kind of the elementary way to say, oh yeah, it must always work, da, da, da. No. We need to show that every single even plus every other even is always going to be even. So we go back to our chart. Let's see how we write an even. We say it's 2m. So instead of the actual number, we go 2m. Then I'm going to add to it another even. Now the temptation is to use another 2m, but that's a little falsehood because we're going to have a 2m plus a 2m. This isn't a consideration to all possibilities. That would be the problem that I want to show. The same even plus the same even is an even. I want all different evens. So I just add a different even. Let's make it 2n, where m and n are any integer. Yes, you have to write that. Every time we do one of these proofs, if you put in an m or you put in an n, you have to write where m and n are any integer. Now, we might have proofs where you want them real numbers, complex, all that stuff, but for now, just integers. And let's simplify this. Well, can I add a 2m plus a 2n? That's 2mn. Wah, wah. No, do not add those. They're not common terms. So I'm still left with 2m plus 2n. But here's my goal. I want to show that it's even. To show a number is even, I need to show that there's a factor of 2. Ooh, a factor of 2. So if I factored this, what would I be left with? 2 times m plus n, which is the form of 2 times something. I like to say it like that. But m plus n can be anything. I don't care what it is. But it's 2 times something, which is always even. It's in that 2 times something form. So we just proved that any even, I don't care if it's 10, I don't care if it's 10 billion, plus another even will always end up being an even number. And that's kind of our simplest case. So that's where these generalities can be used. So here's your challenge or an extra portion of your homework for tomorrow. We have this situation. Okay, we have a trapezoid. We are giving you that this is parallel to this. Doesn't really matter too much in the problem, but you do know it's a quadrilateral with a base 1 and base 2. If you remember, and if you don't, that's okay. What I love about 3x is a lot of times we don't remember a lot of the formulas, but then we can be like, oh yeah, I could actually derive it. I can actually work with this. The area of this is 1/2 base 1 plus base 2 times the height. What I want you to do for tomorrow is see if you can actually see why this works every single time, no matter what base 1, base 2, and the height is. You are free to draw as many lines as you want. You can break this up into different shapes, hint, hint, that may help you get there. But try and rework why this works every single time. Okay, break it up into different sections and try and explain why you're doing your steps as much as possible. Okay, good luck, have fun, and I'll see you tomorrow.